Hi, my name is Jan, and I'm very happy to present our work with the title Weakly Supervised Learning of Rigid 3D Scene Flow on behalf of my collaborators, Andreas, Leo, and Olga. 3D scene flow estimation is a task in which we are given two point clouds x and y acquired by the same observer in two different time steps. The goal is then to estimate the 3D displacement or velocity vectors v such that when v is added to x, this results in a point cloud that is approximately aligned with y. Note that the equivalence is only approximate because the points of both epochs are not in direct correspondence. Fully supervised training of 3D scene flow estimation networks necessitates dense supervision in the form of 3D vectors, which is hard to acquire and is prone to annotation errors. As a result, many recent methods have resorted to training on synthetic data, such as flying things 3D, and then directly generalizing to the target domain of autonomous driving. Yet this comes at a price of a non-negligible domain gap. Other methods have attempted to solve the problem in a completely unsupervised manner, however, they failed to provide competitive performance. We base our approach on an observation that scenes can be decomposed into agents that move as rigid bodies. Instead of predicting the unconstrained flow, we can therefore predict object-level rigid transformations. This object-level representation has several desirable properties. First, it prevents the physically non-viable flow estimates, which might cause a car, for example, to split in half. Second, it provides us with a more holistic representation of the scene, which in turn enables test time optimization of the predicted scene flow. Finally, it enables us to relax the dense supervision requirements. On the right-hand side, you can see that the previous methods are either fully on or unsupervised. Our method, on the other hand, takes the best of both worlds and requires only weak supervision through the background segmentation mask and ego motion, which enables us to use large data sets of autonomous driving for training. In order to obtain the object-level transformations, we devise a network that has to solve multiple tasks. We therefore formulate its architecture as a combination of the shared backbone and task-specific heads, and train it in a multitask setting. The first task is to split the movable foreground objects from the static background. The motion of the static background can then be explained by the ego motion, which we estimate through the differentiable registration in our ego motion head. For the foreground points, we first estimate the unconstrained flow, similar to the traditional methods. However, we also add the foreground instance clustering head, which we realize with a non-differentiable dbScan to avoid requiring instance labels. While dbScan is not differentiable, we can use the recovered object masks to propagate the gradients to their corresponding features. Additionally, we use the masks to index the unconstrained scene flow estimates and compute the rigid body transformations which best explain the underlying flow. Our network is trained in an end-to-end manner using a combination of three loss terms. We evaluate our method on the real-world LiDAR data from autonomous driving using the LiDAR-Kitty dataset. In the table above, you can observe how the traditional fully supervised methods cannot generalize to the LiDAR point clouds of the Kitty dataset. On the other hand, by training in a weakly supervised setting on the target domain, our method can achieve much lower endpoint error, as also visualized in the middle column of the bottom figure. Additionally, we evaluate the generalization capacity of our method on the Waymo Open dataset. Next to the appearance gap due to the different LiDAR sensor, there is also a content gap between these two datasets, as Waymo Open has much more foreground objects, which are also larger in size. This results in the drop of foreground recall when performing direct generalization. However, the performance can be recovered after a short fine-tuning. Through the notion of object-level rigidity, our method is also capable of estimating the flow vectors of very challenging ground points. Finally, as can be observed in the zoom-ins of the middle column, the traditional methods might estimate physically non-viable flow estimates in the ambiguous cases, which causes the card points to completely deform. For more results and interesting ablation studies, please visit our project website. If you would like to discuss this work or other 3D vision problems further, you can also contact me directly using the contact details provided on this slide. Thank you for watching.